All right, let's go over this, go through this really quickly. Does anybody know what this molecule is called? So this is the molecule styrene. Some people have heard of polystyrene. Have you heard of polystyrene? No? No? So polystyrene is a polymer, like all the foam dinner containers. Those are all made of polystyrene. The soft foam cups, right? Those are all made of polystyrene. So pretty important monomer, pretty important polymer that it contributes to. One cool thing about styrene is that you can functionalize styrenes, right? Put different groups on the other side of the ring and give that polymer some functionality, right? So when we do this polymerization, we're going to actually make a copolymer between two different styrene monomers, right? This parachloromethylstyrene and just regular styrene. If we put them in there in a 3-to-1 ratio, we would expect that the polymer would have 25% of its units looking like this, right? And 75% of its units being unfunctionalized. All right, mechanistically, to build this, we're going to start with the terapeutical peroxide, break that apart in our radical initiation process. Radical will add to the styrene, break the pi bond, and then one pi electron will end up in the benzyl position, stabilized through conjugation with the ring. So we have our two carbons of the styrene of the double bond A and B. You can see that oxygen is bonded to carbon A, right? And then carbon B right outside the ring against the single electron. Right? Once we form that one radical, this is just going to keep going in a chain reaction where we're adding that radical to other styrene monomer units. So we just added another monomer unit, right? Here's the carbon-carbon bond that was made. So between the benzyl carbon of one styrene unit, right, and then the beta carbon of another styrene unit. So if we call these A and B like I did above, this would be A and B, right? And this would be another A, another B. Right? And so what this is, I mean, this is going to go on and on until the polymerization stops. And so the polymer that we would make, we're going to include both of the monomers that we're starting with. represented like this, right? Showing that we have in this polymer, 75% of the monomer units are going to be from regular styrene, 25% or 1 in 4 of the monomer units are going to be from this chlorinated toluene. And so when we show the polymer, we need to show that breakdown, right? So we're showing 3 styrene units. So A, E, right? And then we're showing how carbon A here is going to attach to a carbon B at the other end. Okay, and then we're just putting an N outside the parentheses to demonstrate that this could be 16 units long, it could be 400 units long, it could be 4,000 units long. Questions about this? So these functionalized polystyrenes are pretty important. So there's a polystyrene that is acidic. So it's a polymer bead that has an acidic functional group on it. And that's going to look like that. So you can imagine if we're polymerizing this monomer, right, we're going to have a bunch of benzene rings with sulfonic acid groups on the benzene ring. It's kind of nice because we have this acidic polymer, but the acid is not dissolved in the solvent. Right? It can donate a proton, but the acid itself, the molecule itself, is a polymer and it won't dissolve in the solvent. Right? So we can functionalize these monomers in any number of different ways to get them to be functional polymers. This polymer that we made up here, we're going to refer to as the Merrifield resin. Right? And we're going to talk about this a little bit today as we look at amino acids, peptides, and proteins. There's like a black market for dry erase markers and dry erasers on this campus. All right. So let's talk about amino acids. All right, and this discussion, so when we're talking about amino acids, amino acid really refers to any molecule that has an amino group and a carboxylic acid group in the same molecule. So our discussion is really going to focus on alpha amino acids, right, which are the amino acids that are used or that constitute proteins, right, that are found naturally in biological systems. All right, so a general structure of an alpha amino acid like this, right? And in humans, anyway, there are 20 naturally occurring amino acids, right? 19 of them have R groups other than hydrogen. Okay, so 19 of them are going to be chiral. We call them alpha amino acids because the alpha is in reference to the carbonyl group of the carboxylic acid. So the R group, the amine group, is alpha to the carboxylic acid group, which is why we call them, or these specifically, alpha amino acids. All right, how many people have taken biochemistry? Do you have to learn the amino acids in biochem?
No.
No?
Where We have the option to. He didn't make it force. He didn't force us to memorize them this year.
We just see a chart and we can be like, oh, that's amino acids.
Okay, so you can use a chart.
Yes.
Okay, that's what I do too. I don't memorize them. I know a few. Okay, so people are kind of familiar with their structure, right? The variety of R groups hanging off of the amino acid. If you're not, right, if you haven't seen any amino acids, we're not going to go over each individual amino acid today, but in the book, take a look at page 540, and that will give you a breakdown of the different amino acid structures, right, and let you see the variety of amino acids that we have. So amino acids obviously contain two functional groups, or all amino acids at the very lowest level contain two functional groups, right? So we have our amine functional group, and we have our carboxylic acid functional group. Right, so at kind of neutral pH, the structure of the amino acid does not look like this, right? But the amino acid is going to be in equilibrium with its twitterionic form. So the amine, we know amines as being basic functional groups, and carboxylic acids as being acidic functional groups. So it should make sense that some proportion of an amino acid, even though we draw it like this, right, some proportion of an amino acid is going to exist like this, where the amine group is protonated, right, picks up a proton from the acid group, and the acid group is deprotonated. Right, does everybody know the pKa's of those functional groups of the two acids in this equilibrium? No? Anybody want to take a guess?
Is alcohol group 16?
The alcohol group?
Never mind.
So if there was an alcohol group in here, it would be around 16. Carboxylic, that's a little strong for carboxylic acid. So carboxylic acids are usually around 5, all right? But the pKa of this carboxylic acid is going to be around 2. Right? And the overall pKa is going to differ among the different amino acids, right? So some amino acids are going to be a little more acidic at the carboxylic acid group. Some are going to be a little less acidic. So the range we usually see is between, I would say, 1.7 and 2.6, right? So we just say it's around 2. All right, and what about the ammonium? What about the conjugate acid of this? Remember what ammonium compounds usually around?
Around like 10.
Good, yeah, it's going to be around 10. These and amino acids, pK is usually around 9. Right, again, that varies roughly between, say, 8.9 and 9.6, right? But just say roughly around 9. Okay, so in this form, pK is 2. This form, pK is around 9. Which way is this equilibrium going to favor? The product, good, Pep. So it's going to favor the weaker acid. And then what's the KEQ? Good. Yeah, so 10 to the negative 7. There, yeah, 10 to the 7. Right, so what this means is that if we had a solution of this in water, there would be 10 million molecules of the ammonium carboxylate to every 1 molecule of the amino acid. So just to bring that into context for you, right? So we talk about these equilibria a lot, right? If it's an equilibrium like 10 to the 7th, we have some huge number on the right, right? Some small number on the left, right? So again, in solution, there's going to be 10 million molecules of this to every 1 molecule of that, right? When we're thinking about number of molecules in a system, and you guys have been doing reactions on 1 millimole, how many molecules are in 1 millimole?
6.022 times 10 to the 20th.
Good. Right, 6.022 times 10 to the 20th, right? So 1 mole is 6.022 times 10 to the 23rd, right? 1 millimole is going to be 6.022 times 10 to the 20th. Just to make things easier, we're going to divide this by 6, 1 times 10 to the 20th, right? So if we have 1 millimole, right, and we have 1 millimole of our amino acid in solution, right? 1 millimole is going to be 6.022 times 10 to the 20th. We're going to simplify it just by saying, all right, we have 10 to the 20th molecules, right? Of those 10 to the 20th molecules, 100 trillion will be in the amine form. Right, 100 trillion of those molecules will be in this form. Right, so we have these ratios, and it seems like 10 million to 1, right? That's a ratio that heavily favors the right-hand side. Okay, but in a reaction, if we have 1 millimole, there's still going to be 100 trillion, or I guess in this case 600 trillion molecules, right, that are in this form. So there's still a considerable amount of molecules in that form, right? Just because we have so many molecules. Okay, so that's important, right, when we have these equilibria. If you think about the enolate equilibrium, right, that enolate equilibrium favored the ketone, right? But if we have 1 millimole of molecules in our reaction, there's still going to be a lot of enolate being formed, right, on the whole. Okay. Questions about that? Okay. So again, just to bring these numbers a bit into a little clearer context. Okay, so the other thing that we have going for amino acids is that all of the amino acids except 1 are going to be chiral. Right, so the nitrogen is going to be sitting on a chiral center, right? For all but 1 amino acid, that chiral center is going to be the same configuration. So all of the amino acids are going to look the same way, right? And the chiral center, the naturally occurring chiral center, is going to be in the S stereochemistry. Okay, 1 amino acid is going to have R stereochemistry. So right, so for example, when R is a methyl group, that's the amino acid alanine, right? And S-alanine is going to have that methyl group, when we draw it in this form, going back into the form. Okay, the 1 amino acid that does not have an S stereocenter is the amino acid cysteine, right? And all right, so this is the structure of cysteine. You can see cysteine has the same configuration, right? Dashed bond, that R group going back into the board. Okay, but it's an R stereocenter. So where does the difference come from? Right? Both of those R groups are going the same direction, but one is the S stereoisomer, the other is the R stereoisomer. Why is there a difference? Joey?
Now the sulfur carboxylate is now the highest priority group.
Say that again?
The bottom group is now the highest priority because the carbon attached to the sulfur instead of not.
Yeah, so it comes in how we're identifying the priorities, right? So R and S are just our way of communicating to each other how to draw a stereocenter, right? On both of these, the highest priority group is going to be nitrogen, right? On alanine, the second highest priority group is going to be the carbon of the carboxylic acid, right? Third highest priority group is going to be the methyl group, and then the lowest priority group is going to be the hydrogen that's coming off that chiral center. Right? When we change that R group to a thiol, right? Nitrogen's still the highest priority group, but now when we look at these two carbons, one is attached to sulfur where the other is attached to oxygen. So this carbon would get the second highest priority, carboxylic acid would get the third highest priority, and then the hydrogen is the lowest priority. Right, so it really comes down to how we account for the priorities or how we identify or name those chiral centers. Right, the configuration, overall configuration is the same with the R group going in the same direction. But because we're introducing a sulfur, right, that's going to change the priority or switch the priority of the second and third groups. Okay, and so as a result, that gives us a different way to identify that center as R rather than as being S. Right? So chiral amino acids, naturally occurring chiral amino acids, for humans anyway, they are all in the S form, right? Except for cysteine. Remember, that's not because we're switching the direction of that R group, it's just because we're accounting for the priorities a little differently. Right, questions about that? All right, so let's talk about peptides. All right, peptides are just the polymers of amino acids. So if we look at the structure of an amino acid, and pay attention to the two functional groups. Okay, we have an amino functional group, which we know means being nucleophilic. Right? And we have a carbonyl functional group. Right? And carbonyls we know as being electrophilic. All right, so when we talk about the polymerization of amino acids, we're talking about the nucleophilic group of one amino acid interacting with the electrophilic or bonding to the electrophilic group of another amino acid. All right, so dipeptide. Right, so this is an example of a dipeptide. Right, here is our critical bond in this dipeptide. So this is what we refer to as a peptide bond. Right, and in this dipeptide bond, this is how those two amino acids are connecting to each other. Right, so the two amino acids that make up this dipeptide are going to be alanine. And phenylalanine. Right, and so the connection that has to be made is that this nitrogen has to add to the carboxylic acid, right, to make that peptide bond. And this happened naturally. Can we take amines and add them to carboxylic acids? Baptiste, you're shaking your head no. Why not?
Because otherwise it would react on our body.
So say that again.
It would react in our body easily, like.
So they don't react easily. So what would be the reaction that would take place if we had just a simple carboxylic acid, say acetic acid, plus ethylamine? What's going to happen if we mix these two molecules together?
The nitrogen will pull the proton.
Good, right? So remember the primary activity of a carboxylic acid is its acidity, right? So the amino group is going to pull the proton. That's the fastest or quickest reaction that's going to occur, right? It will form the carboxylate and the ethylammonium salt. Okay, so when we think about peptides, right, we can draw the constituent amino acids, but they're not coming together in that simple of a fashion where we're just taking two amino acids, mixing them in a round bottom and expecting them to react with each other. Right? The only chemistry that can really happen under those conditions is acid-base chemistry. Okay, so when we're thinking about the synthesis of peptides, it's a little more complicated than just mixing two amino acids or multiple amino acids together. All right, so we could have, peptides, we could have dipeptides, tripeptides, tetrapeptides, right? Once we get beyond a certain number of amino acid residues, we just start referring to those molecules as polypeptides. Right, and these are just going to be long amino acid chains. Right, and I'm not going to draw out a polypeptide. We know kind of how peptides form through these peptide bonds. So you can imagine, getting 100 amino acids in a long chain, what that would look like. So here's polypeptide. We have 5 amino acid residues. All right, and I'll identify all of the amide bonds we have in this polypeptide chain. Right, so you can see that we have 4 different amide bonds that formed among the 5 amino acid residues. Right, in this polypeptide, we can identify one end versus the other end by referring to the end that has a free amine as the N terminus. Right, and then the other end that has the carboxylic acid we refer to as the C terminus. Okay, so when we're talking about the peptide, we're referring specifically to the chain. What is a protein? How are proteins and peptides related to one another?
It's when the protein has a shape.
Good. So what,
The peptide has a shape is a protein.
yeah, when the peptides, so these peptides, you can see these peptides are full of hydrogen bonding donors and acceptors. Okay, and so these molecules, these long chains, right, they don't necessarily want to be floppy, and so they're going to start folding onto each other, right, mostly through hydrogen bonding interactions, intramolecular hydrogen bonding interactions. And so a peptide becomes a protein whenever that long chain folds in and forms some low energy folded structure. Okay, so proteins are just folded peptides that folding is largely governed by hydrogen bonding. And other intramolecular forces. Right, and then most proteins are going to have some specific function, right? They're going to be receptors, small molecule receptors. They're going to have some structural function. So our skin, right, is composed of proteins. Muscle is composed of proteins, right? Specific proteins that you guys have heard of before, enzymes. Right? How do enzymes function? So enzymes are specific types of proteins. How do enzymes function?
Enzymes have a specific active site where some other enzyme or something else could fit in there.
Yeah, so there's some active sites. So usually we refer to a molecule as an enzyme if it catalyzes or promotes a chemical reaction. Right, so enzymes are proteins that catalyze or facilitate a chemical reaction. Right, most enzymes will end with the suffix ase. So you've heard of kinases, esterases. You heard these terms before? Yeah. So let's talk about peptide synthesis in the laboratory, right? So I already said that if you take two amino acids and mix them together, nothing's going to happen other than some acid-base chemistry, right? But imagine that we had a method that allowed us to take two amino acids and react them together to make a dipeptide, all right? What would be the problem of just taking two amino acids, mixing them together, and making a dipeptide? What complications would we run into here? Other than the fact that these on the surface, these are not going to react with each other. Imagine we had some magic reagent that allowed that reaction to occur. Sarah?
You can't just stop two of them from interacting with each other, but all can interact.
Good, they're all going to interact, right? So from these two amino acids, we can make 4 different dipeptides, right? We can make a dipeptide, so imagine that if we had, we could make an alanine-alanine dipeptide, right? We can make an alanine-phenylalanine dipeptide. We can make a phenylalanine-alanine dipeptide, and then a phenylalanine-phenylalanine dipeptide. Right, and we're assuming that the residue on the left represents the N-terminus, and the residue on the right represents the C-terminus. Right, so from those two amino acids, we can make 4 different dipeptides. Yeah.
And when we can do an infinite quantity, like alanine.
Oh, you can, yeah. So I'm just saying to keep things simple, right? To keep things simple, we're imagining taking 2 amino acids and just making a dipeptide from them, right? So you're right. I mean, usually when we do amino acid synthesis, you have to be mindful of the fact that these are polymer, these can polymerize. Yeah. Okay. So that's the problem that we present, right? And so synthesis has a way to get around that. Looks like we're out of time, so we'll come back to this on Friday. If you have a chance, so this is all in the book, right? If you have a chance, read through this section in the textbooks, chapter 24, right? It's literally 2 pages. Get a preview for what we're going to go over on